Okay, so welcome again to the course Fundamentals of Solar Photovoltaics and Technologies. So we will look at lecture number 6 today, in which we will talk about solar radiation, especially looking at geometry and the geometrical factors of solar radiation with respect to the surface that we consider, and quantitative determination. So just to briefly recap what we discussed earlier. So we discussed solar radiation, which is from the solar radiation that is incident from sun on earth. We can determine how much is the amount of solar energy that we get on a said surface. We saw that spectral irradiance that we obtain on the earth is dependent upon the wavelength, and it maximizes in the visible region, that is between 300 to 750 or 800 nanometer. There is a huge difference between what we get at the outer fringes of Earth's atmosphere and then on the surface, and this is mainly because of absorption losses that occur while the sun rays travel from the fringes of outer atmosphere to the surface, and this is mainly because of absorption by various entities, and one can also see the absorption bands because of things like moisture, oxygen, ozone, carbon dioxide, etc. in the solar spectra. So atmosphere plays a very important role in determining the losses. So on a clear day, your radiation that you will receive on a given surface will be very high as compared to than on an overcast or cloudy day. The solar constant that we saw at the outer surface, solar constant is 1367 watts per meter square. That is the value that is the value of extraterrestrial radiation that we receive on the outer surface, and this goes down in the value as we receive on the surface because of atmospheric losses. Air mass is the quantity that we considered as one measure of one tool to quantify the losses, and typically for countries like India, countries which are above equator in the northern hemisphere, unless they are on poles or temperate region, we use a factor of AM 1.5, which is a common method for quantification of solar radiation. So whenever you will always see for characterization we use AM 1.5 G. So AM 1.5 sort of approximates the average radiation that you will receive throughout the day, average of the radiation that you will receive throughout the day, and G means global, which means it will consider both direct and indirect radiations. Having done that, we then moved on to understand the concept of solar time, which is mainly because of the differences which are between the local time and the standard time, and this is because we consider countries as one time zone. So for example, India falls in time zone of 5:30 hours ahead of GMT because we consider countries as one time zone. So for example, India falls in time zone of 5:30 hours ahead of GMT, Greenwich Mean Time, but whole of India does not have same time locally speaking. Western part of India has very different time as compared to eastern part because of the position of the sun. So the solar noon and the real noon, or noon according to watch, is very different, and that needs to be accounted for in order to calculate the real times according to the real position of the sun with respect to that location, and making those correction factors in various calculations. So today we look at what we call as solar radiation geometry, and this is essential to understand, to determine the solar energy that falls on a given surface of a particular orientation at a given location. If you wanted to, let's say your location is Bombay, and your solar panel is at a given location, let's say 45 degrees with respect to the horizontal, and what is the amount of solar energy that will fall on a given surface? That is the idea of this exercise, to calculate that energy. And basically we want to convert the value of radiation from the direction of sun into an equivalent value which is corresponding to the surface normal. How much is the value that we get on the surface normal? So let's say in this picture we see that this is a horizontal plane, the gray one. On the horizontal plane we have a panel, let's say, which is at certain angle theta, beta, let's say this is the angle beta. So there are and these arrows depict north and south of the plane, and you can obviously say this is east and this is west, and the panel is at an angle beta to the horizontal plane. So, you can see that this, the black one is the horizontal normal. So, this is the normal direction to the horizontal, and the blue vector or blue arrow points out the normal to the surface, and then sun beam comes at a certain angle to this surface normal at an angle theta. So, the angle between the sun ray and the horizontal normal, as we know, is zenith angle. So, we can say this is theta z, and this angle between the surface normal, the plane normal, you can say, not the horizontal plane, but the plane on which the beam is falling, let us say the solar panel, and the sun ray is theta, and our intention is to calculate these values to help us assist in calculating the exact value of solar radiation that falls along the surface normal of that plane, that particular panel. And this is why we need to have knowledge of different solar angles, which will come handy in calculation of this whole exercise. So, let us say first the motion of sun. So, if we, let us say this is our plane of earth on a given, and let us say this is my east direction and this is our west direction. So, consequently, this becomes north and this becomes south, and we know that sun in the morning it rises on the east. So, this is in the morning, and in the afternoon it will go. So, this is morning, sunrise, and this is sunset. So, you can say sunrise. Okay. For the, depends upon the hemisphere you are in. For the southern hemisphere it will go northern part. So, it will the path that it will track from north east to west, it will be northish for the southern hemisphere. So, if you are in southern hemisphere, that will be the situation, this is the path that it will take, and if you are for northern hemisphere, and for the northern so let us say I make this earth as green, okay, for the sake of illustration. All right, and for the northern hemisphere, if I have to track, then sun will be, and it follows a path which is southish. Okay. So, depending upon where it is, it will cast a. So, if you have an object, let us say you have a tree at a given position. This is the tree that we have, and if we are in southern hemisphere, then this tree will have a shadow, something like that, you know. So, this is the tree or object, this is the shadow. So, because it is going a little northish, and shadow will form on the other side if you look at the northern hemisphere. So, this would be your northern hemisphere. Okay. So, basically let us say if we have a surface, let us assume a surface which is something like this, and this is the surface normal n, or just say normal because n can, and this is your sun from which, and this is the angle theta that we talked between the surface normal on which the solar radiation is falling with respect to the direction of solar beam. See, yeah. So, I have jotted it down. So, if theta is the angle between sun's rays and the module surface normal, then the motion of sun with respect to surface normal will determine the amount of power that we will receive on a given surface. If sun's ray is perpendicular to absorbing surface, then theta is equal to 0, which means the intensity that we will receive on the surface will be maximum intensity, which means when it is at zenith. and when sun rays are parallel to the surface, that is 90 degree, which means it is parallel to the surface, we will get nothing on the surface, which means I is equal to 0. And for any angle that is between, let me just wipe this out. So, for any angle that is between 0 to 90 degree, that is when it is travelling from east to west, I will be I max cos theta. So, that is how we can determine intensities at given angles, but for that first we need to determine the angles, I mean with respect to other factors. So, the first thing that is important to learn is declination. Declination is important to understand because Earth rotates around an axis which makes an angle of about 66.5 degrees with the plane of its rotation around the sun. So, if this is your let us say this is, let me choose appropriate color. So, let us say this is Earth, okay, and let us say this is the north south, okay, and this is the equator east west. So, this will be your equator, okay, and the sun rays are coming from this side. So, this is your sunlight. So, if you now, so you can say that this is my axis which is parallel to sun rays, okay. And if I draw a vertical line here, then this angle between, so this the sun ray is basically, you can say, is the direction of ecliptic plane. So, the angle between sun rays and the equator is called as delta, and likewise this angle will also become delta. This is the declination angle, and because, so we are saying this 66.5 degrees. So, of course, it is 66.5 degree so basically you can say this angle will be 66.5 degree. So, this will be in fact 66.55 degree and this will be 23.45 degree. So, the maximum now because it's the axis of Earth's rotation is tilted with respect to ecliptic plane, when it rotates around the sun there is a effect of seasons. So, when you, so let us say this is your this is where we have sun in the middle. So, this is sun, okay, and it is rotating around. In fact, it's I have drawn it a little smaller, but you can draw it a little bigger also, maybe something like that, okay. Okay, and your Earth is rotating somewhere here with a bent axis. Okay. So, it follows different angles on different times of the year. So, for example, in December 22 we have what we call as winter solstice when delta is equal to minus 23.45 degree. That means the shortest day for the northern hemisphere. So, we are talking in terms of northern hemisphere. And when it goes to June 21 to this side, then we have summer solstice and delta is equal to plus 23.45 degree. Okay. And then somewhere here we will have March 22 and this is where we will have September 22 or 23 I think. This is equinox and this is, which means delta is equal to 0 and delta is equal to 0. So, basically the value of delta changes from minus 23.45 to plus 23.45 because it is orientation dependent. So, on one side when it comes it is tilted like that, when it go to other side it becomes tilted like the other way around. So, because of this seasonal changes, because Earth's axis is tilted at an angle of approximately 23.45 degrees with respect to its orbital plane around the sun, and basically this is why we have changing seasons. We have shortest day in winter, we have longest day in summer, and we have these equinoxes when day lengths and night lengths are equal, and this is what causes changing seasons, winter and summer and so on and so forth. So, basically you can say delta varies from plus 23.45 degree. This is the angular range it varies in, and that is why we get, because of this tilt of Earth's axis around the ecliptic plane, this is why we get differences in seasons, shorter day, longer day, and so on and so forth. In this figure, of course, this is your Earth. We have north celestial pole and south celestial pole, and we have kept Earth. So, you can say, you can depict the same diagram as if sun is rotating around the Earth, or you just have to choose a right reference point. So, here we have kept the Earth at the center, and this is your equator at 0 degree, and this is the ecliptic plane. So, the angle between these two is basically, you can say, is the delta. So, this is what it will be. So, basically angle between the equatorial plane and angle between the ecliptic plane, and we can define this angle as delta is equal to 23.45 degree multiplied by sine of 360 divided by 365 into n plus 284. You can also make it n minus 81 because 284 plus 81 will be 365. So, you can write it either n minus 81 or n plus 284, both of them are correct, they will give you the same answers, and this basically give you the value of. So, what it depends upon is only the day of the year. So, if you know the day of the year, you can calculate what the declination angle will be, and declination angle, again it is the angle made by joining the by the line joining the centers of the sun and center of the earth. So, angle, the line that connects the center of the earth and center of sun with its projection on the equatorial plane. In other words, it means that it is the angle between the equatorial plane and the ecliptic plane. Okay? That is what it means. So, basically you can say that when delta is equal to 0, if this is your earth, this is your equator, and it is rotating something like this is north, this is south, and if solar radiation is coming like this, then this is your east, west. In this case, what will be delta? Delta will be equal to 0 degree. Okay. And for another case, when sun rays are coming like this, and if it's again, we make a circle here and we make this angle, we make this, it has rotated, right. So, now this is your east west, the angle between this is given as delta, and this will be your delta is equal to plus 23.45 degrees. Okay. And you can make the same picture again, and if it becomes like this, this is north, this is south, east, west, and if your sun rays are coming from this side, then it has become delta is equal to minus of 23.45 degrees. Basically, you can say your delta will change if you plot, for example, this is December 21 and this is again December 21, then it will go through change like this. Okay. So, that will be minus 23.45 and this will be plus 23.45. So, this will be summer solstice, this will be winter solstice, somewhere in between we will get 0 when we have equinoxes. Okay. So, this will be your June, right, and as you go to December, this will be March and this will be September. Okay. Now, let us look at one more angle which is called as elevation or zenith altitude angle. This is represented by alpha. This is the angle between the sun ray and its projection on the horizontal plane. So, naturally what it means is that alpha will be equal to 0 when sun is at zenith and it is 0 when it is at sunrise. So, let us see how does it get depicted. So, this is your let us say so this is east and this is west. Okay. And let us define the path. This is the path, and if this is the sun on top, okay, and this is what my and if sun ray is coming at this point, this is the projection on the horizontal plane. So, the angle between these is, so this is your what we call as projection on the horizontal. This is sun ray, this is horizontal, and this angle is nothing but alpha. And as the sun varies, so of course, when it comes on top, it is directly coming directly on the along the normal, which means alpha will be equal to 90 degrees, and when it is at the when it is in the east and west at sunrise and sunset, then alpha will be equal to 0. Next angle that we consider is zenith angle, that is the angle between the sun ray and the horizontal normal, and this we can say is something like this. So, this is our sun, okay. And let us say, so this is what we call as is the zenith angle, theta z. So, naturally this will be your alpha. Okay. So, this will be nothing but alpha. So, theta z is equal to 90 minus alpha. All right. And the other angle that we consider is solar azimuthal angle. So, again this is the angle which is made in the horizontal plane between the north south line and the projection of sun ray on the horizontal plane, that is minus 90 to plus 90. So, let us say this is what is the horizontal, east, west, north, south, okay. and we have sun somewhere here, okay, and this is where we have. So, this is your array, this is the projection, okay, on horizontal. So, what we are saying is that angle made in the horizontal plane between the north south line and the projection of the sun ray on the horizontal plane, which means it has to be an angle between this and that. Okay. So, this angle is called as gamma s. Okay. So, it goes from plus 90 to minus 90 depending upon which side you are on, whether you are in the east or whether you are in the west. Okay. Putting it all together, this is how it looks like. So, this is a picture which is taken from the book Solar Energy by Sukhatme and Nayak. So, let us say we have this horizontal plane, and on this we have a surface which is kept in angle beta. So, this is the sun, sunbeam is coming at an angle theta with respect to the normal of the tilted plane, which is this, theta is the angle, and naturally the angle between the surface normal, the horizontal normal, which is the zenith, and the sun will be theta z. So, this is your zenith angle, okay, and this will be your solar altitude angle, which is the projection of sunbeam on the horizontal and the sunbeam. This will be alpha. So, alpha and theta z will always be 90 degrees, and of course, you can calculate what is and the angle between this line, that is this line, and the north south line is gamma s. This is what gamma s is. Another angle that we would like to depict is called as gamma, which is surface azimuthal angle. So, beta is the angle which is made between the horizontal plane and the surface, or you can say the angle between the both the normals. So, if you take the angle between these two normals, this will also be beta, right. Similarly, so this is the angle made by the plane surface with the horizontal. Gamma is an angle which is called a surface azimuthal angle, which is the angle made in the horizontal plane between the line due south. So, this is the due south line and the projection of the normal to the plane on the horizontal plane. So, this is the normal to the plane, its projection is this. So, basically this is an angle between this and that. This is gamma surface azimuthal angle. So, this is gamma s is solar azimuthal angle, that is between due south and projection of solar beam on the horizontal, and gamma is the surface azimuthal angle, which is the projection of surface normal on the horizontal with respect to due south. Okay. So, this is the difference between the two, and theta is the angle between the sun ray and the normal to the tilted plane. So, this is what it sums it together. So, we can say that declination angle is 23.45 sine of 360 by 365 n plus 284 or n minus 81. From this we can determine what declination angle is. It should always be between plus 23.45 to minus 23.45. And I have not done this calculation, but if you go to this paper by Brown and Mitchell in 1983 by spherical trigonometry, considering earth is a sphere and so on and so forth, you can determine what this angle cos theta will be. Cos theta is a function of the phi, which is the latitude, the delta. So, this is latitude, delta which is declination angle, beta which is the angle between surface and horizontal, gamma which is the surface azimuthal angle, omega is the hour angle, that we discussed, that depends upon the time of the day, everything else is known. So, everything here is known depending upon the time and day of the year and the location. So, gamma, so this factor takes care of the location, that is city or place. This factor takes care of the day of the year. This factor takes care of the position of surface with respect to horizontal, and this factor again takes care of the position with respect to the due south. So, these two are the position factors, and then our angle takes care of the time of the day, because it will also vary as a function of time. So, all these angles which we know can be used to determine what theta is. So, if we know theta, then we can determine what is I cos theta. Okay. We still do not know how to determine I, we will see that later on, but we know how to determine cos theta at the moment. So, we can approximate this cos theta for variety of cases. For example, for a vertical surface where beta is equal to 90 degree, cos theta can be simplified because all the cos beta terms will become 0. So, this equation gets simplified to this form. For a horizontal surface, it becomes even easier because sin beta becomes equal to 0. So, it just boils down to sin phi sin delta plus cos phi cos delta and cos omega, and for a horizontal surface the angle theta will become zenith angle, okay, because both the surface normal and horizontal normal will remain the same. As a result, theta will be nothing but theta z. You can further simplify it if a surface faces south. If a surface faces south, which means surface azimuthal angle will become 0, because that is the angle between the due south line and the projection of surface normal on the horizontal. So, that angle becomes 0, gamma becomes equal to 0, and then cos theta becomes sin delta sin phi minus beta plus cos delta cos omega cos phi minus beta. So, we can basically simplify these equations further. We can also express these in terms of other angles. So, for example, for a horizontal surface we know that theta is theta z. So, you can replace theta by theta z and do these. These angles can be manipulated and represented in different ways. So, we can represent theta in terms of theta z, slope, azimuthal angle and solar azimuthal angle. So, different ways of depicting can be found, but the fundamental equation remains the same, which is this equation. You have to work out for a given situation as a reduced equation from this main equation. Okay. So, basically by using these equations you can calculate what is the value of theta. Okay. And for a given we can also determine solar azimuthal angle as cos theta cos gamma s is nothing but cos theta z sin phi sin delta minus sin delta divided by sin theta z and sin phi. So, all these angles will help you calculate what is theta. Another thing that we need to know for calculation of radiation, for example, throughout the day, we need to understand what is sunrise and sunset and day length. So, for a horizontal surface we can find out the hour angle corresponding to sunrise or sunset by substituting theta z is equal to 90, because theta z will be 90 because the beam is parallel to the horizontal. As a result, theta z is 90. So, if it is 90, we can say cos omega s corresponding to sunrise or sunset is minus tan phi tan delta, or omega s is cos inverse tan phi minus tan phi tan delta, and the values will depend upon sunrise and sunset, positive for sunrise and negative for sunset, and maximum day length will be the difference between sunrise and sunset. So, it is basically omega s minus of minus omega s, that is 2 omega s. So, basically it is 2 divided by 15, and 15 is the angle per hour, angle covered per hour. So, 2 divided by 15 cos inverse minus of tan phi tan delta. So, essentially you can say this is nothing but omega s minus of minus omega s, and this takes care of 15 degree per hour. So, this is your day length, and So, between for the southern hemisphere between March 21 to so your sun will be very south when it is winter and it will be north when it is summer. So, between March for the northern hemisphere between March 21 to September 21, the sun will move north of east west. So, it will move from south towards the north. So, certain corrections need to be made. As a result, the omega s in that case becomes cos inverse minus of tan phi minus beta tan delta. So, some corrections need to be made. So, basically sunrise you can say will be 12 minus whatever the omega s, 12 is the noon time, right, 12 is the noon time. So, 12 minus whatever the sunrise hour you calculated, that will give you the sunrise time, and 12 plus will give you the sunset time, and you also need to apply the time correction depending upon the local situation, whether it is what is its lambda with respect to standard lambda. So, you need to make the time correction. So, basically this is 12 noon. So, with respect to noon, by adding or subtracting omega s, and this is nothing but omega s, right. So, how many hours behind 12 or how many hours ahead of 12, that will give you the exact sunset time or sunrise time in hours, and you need to apply time correction for differences in lambda with respect to lambda standard. Okay. So, we can do some calculations. I will go through one problem in the next class, and in the next class then we will also see how we can measure the radiation. So, we will stop here. What we have learnt is we have learnt about the solar geometry, learnt about different angles such as declination angle, zenith angle, solar altitude angle, solar azimuthal angle, surface azimuthal angle, and finally how you can determine the angle between the solar radiation and the surface normal, which is important to calculate the amount of radiation that will fall on a given surface, and we can see that it is a function of the location which is determined by the latitude. It is also a function of day of the year, it is a function of time of the year, and the inclination. So, these factors put together can help you calculate the angular relation. And now, next class we will do one problem, and then we will see how do we also determine the value of radiation itself to finally determine what is the value of radiation that falls on a surface. Thank you.